Hello and welcome to my Discrete Math problem 3.19. My name is Ilyas Belarabia and let's get into it. The problem shown in the book as find a necessary and sufficient condition on the real number b bigger than 1 such that the floor of log base b if x is equal to floor of log base b if floor x for all real x is bigger than or equal to 1. So the first stuff that we're going to pay attention to is that what we're mainly trying to restrict is b, so x can be any real number bigger than or equal to 1. The other thing that we're going to be looking for or looking at is the notion of a necessary and sufficient condition. When I first looked at it, it felt like a weird thing to say on a math problem. And when I was on a call with Miss A, she told me to pay attention to necessary and sufficient. So I went ahead and just Googled it, and I discovered that the term sufficient and necessary condition is actually a mathematical concept that can be summed up in a term that we use very frequently, which is if and only if. And I'm pretty sure that you might have encountered it at a certain point in your math classes. Basically, it means equivalency. So a term has to exist. If a term exists, that means that the other term has to exist as well. So first, we must establish necessity, then sufficiency of our condition on the real number b bigger than 1. So first of all, what I did was I plugged in the logarithm in Desmos and graphed it using different bases to see how it's going to play out and what it's going to give me. So I did a lot of these, but I only showed two cases, log of 3, log of base 3, and log of base 3.5, in order to make this video shorter, of course. And I took these three values for each of them, and I played around with them and discovered that the theory that we're trying to prove that we have only works if b is an integer. So in case of log 3 it works, but in case of log 3.5 it cannot work. It does not work. So I know this, but I don't know if this is a sufficient or necessary condition. I still don't know it yet. It's just something that I came upon. So the next step would be to verify if it's a necessary condition and a sufficient one. First, we start with necessity. We will try and prove that if b is an integer, and this is what this symbol means, it means b is an integer, it implies that the floor of log base b x is equal to the floor of log base b floor x. So we will take that b is bigger than 1 and b is an integer. If it works, it should adhere to the theorem 3.10 in page 71, which states that the floor of a function f of x is equal to the floor of function f of a floor x, and also works for ceilings too. And this theorem only works if two conditions are met. So if a function f of x is equal to logarithm base b of x is an integer, if this is an integer, then it has to imply that x is also an integer. This is the first condition. So let us define f of x as log base b of x, with x being a real number that's bigger than or equal to 1, and b being an integer. If we assume f of x to be an integer, then log base b x is an integer as well, using equivalency here. So log base b of x is bigger than or equal to 0, and since the lowest value x can be is 1, as shown here, it's going to be bigger than or equal to 0. And we know that one of the properties of logarithms is that it is monotonically increasing. Now, b to the power of log base b of x is an integer, since b is an integer, as we mentioned before, and log base b is a non-negative integer, as we have mentioned before. As we have mentioned here, if log base b of x is equal to 0, then b to the power of log base b of x is going to be equal to 1, since this is going to become the power. Otherwise, log base b of x is going to be a positive integer, as we mentioned. So Since b to the power of log base b of x is equal to the x, and we've already established that b to the power of log base b of x is an integer as well, we can conclude that x itself is an integer. Therefore, we have proven the first condition for the theorem, which is that if we assume function x is an integer, therefore it will imply that x is also an integer as well. Now, the second condition is something that we've already established when we were looking for the first condition, is that since function x is logarithm base b of x, and we know that one of the properties of logarithms is it increases monotonically and it is also continuous over the domain, therefore f of x also increases monotonically and continuously over its domain, which is x is bigger than or equal to 1. So in conclusion, since we proved the two conditions to prove the theorem 3.10, therefore it means if we replace f of x with what we defined it to be, therefore floor of log base b of x is equal to floor log base b floor x. Therefore proving the necessity of the condition that b is indeed an integer. Now we have to prove the sufficiency of this condition. So we're going to have to prove that the floor of log base b of x equals the floor of log base b floor x implies that b is an integer. Now this can be kind of complicated, so one of the ways to make it much more simpler and easier to do is to try and prove the opposite of it. So if you can disprove the opposite of it, that means that it is possible, and if you prove the opposite, then that means that it doesn't imply that b is an integer. So we're going to take that our theorem implies that b is not an integer. So we know that log base b of b is going to be 1 since base and x are b. Therefore, using this theorem, floor of log b base b is going to be 1 floor is going to be 1. And since b is an integer, floor b is going to be less than b, of course, as stated by the rules of floor. So b is going to be unequal to floor b. And since log are monotonically increasing, log base b of floor b is going to be obviously smaller than log b of b, since floor b is smaller than b. So we already established that log base b of b is equal to 1. Therefore, log base b of floor b is going to be less than 1. Therefore, log base b floor b is going to be less than 1, as proven here. So, using theorem 3.7a shown in the book, if x is smaller than n, then the floor the floor of x is going to be smaller than n as well. So we get log base b of floor b is less than 1, therefore floor log b of floor b is less than 1 as well, which contradicts what we shown earlier, which is that it is equal to 1. So this contradicts what we had earlier and gives us that our theorem is wrong if b is not an integer, therefore proving the sufficiency of our condition that b is indeed an integer. I hope you understood, and thank you for listening to my presentation.